Man has often dreamed of sailing the stars and cultivating some far-off land. CitizenCon 2024 showed an in-depth look at how that might look in Star Citizen. The idea of terraforming isn't unique to one game, however. So let's talk then about how we might actually do this in the real world. To start, let's look at our own solar system and explore the solutions to conquer our neighbors before looking further afar, for democracy. The first major obstacle that any terraforming venture has to overcome is the primates conducting the activity.
Look. Oh shit.
Our fleshy meat sacks come with a long list of constraints that have to be respected. Obviously, we need water, but for the purpose of terraforming, this isn't as hard as some of the other constraints. While water is necessary for discovering life on other planets, it's not a prerequisite in the same way with intelligent life forms on site that can manipulate the environment directly. In much the same vein, a breathable atmosphere lies on about the same difficulty as water. For evidence of this, we have two examples that I'd like to look at for some real-world context: submarines and the International Space Station, or ISS. In a submarine, while you do have the capacity to surface or breach and replenish your air supply directly from our native atmosphere, you don't always have the ability. There may be an opposing force hunting you, and breaching the surface would be a clear giveaway of your position. In these cases, what kinds of systems do submariners have at their disposal to keep breathing? One of my favorite YouTubers, Destin from Smarter Every Day, made an excellent video on the topic, and I'd highly recommend checking it out for a more in-depth look at the problem. This video will take a more summarized approach. In the case of a submarine, there are two primary ways to create oxygen: electrolysis and oxygen candles. In the case of electrolysis, electric current is run through water to separate it into oxygen and hydrogen. Care needs to be taken to limit the reactants that are present, as using salty seawater, for instance, will result in the production of chlorine gas. On the submarine, they control this by using reverse osmosis to filter for pure water, and then they add potassium hydroxide as a catalyst. This results in pure hydrogen and oxygen gases with harmless byproducts. The uses for oxygen are obvious. It's what we breathe. But hydrogen is also very useful. If you were depending on electrolysis to produce your atmosphere, it's beneficial to also store the hydrogen for its industrial potential. Electrolysis is the primary means that nuclear submarines employ, as they have a relative abundance of electrical power. In cases where electricity isn't an option, though, what do? That's where the oxygen candle comes into play. Composed of iron oxide and sodium chlorate, when ignited, it results in more oxygen than is occupied in the combustion reaction. So you get a net increase of oxygen. These are relatively safe and easy to accommodate, but as a self-oxidizing fire, they're not without risk. Unless you have the means to manufacture more of them on site, they are also one and done. A colony ship would be well served to bring a host of oxygen candles with them for emergencies, but they would not be a sustainable way of creating a breathable atmosphere. If your destination has an abundance of liquid water, then electrolysis is a relatively simple way to create your needed oxygen. But as you may already know, finding water on other planets is quite the challenge. So just like the candle, you shouldn't rely on finding water. You're going to need to get more creative. The other part of atmosphere maintenance is getting rid of the CO2 that the primate crew is producing. On the submarine, they use a chemical called MEA that can be continuously cycled through a heat and pressure system to absorb CO2. The other principal method is lithium hydroxide canisters that act passively with airflow. These have similar trade-offs as the oxygen production. One requires continuous power, and the other can only be used once before the canister is expended. Since the submarine can rely on at least periodic atmosphere refreshes, the scrubbed CO2 from the internals is simply jetted out of the sub. In the case of our terraformers, they can't afford to waste anything, so cycling the CO2 will be important for other processes. Setting our sights even higher to the ISS, things are surprisingly similar to our submarine. At the outset of operation, compressed gases were literally shipped to the ISS via shuttle. More recently, the ISS uses a similar electrolytic process to generate oxygen from water. There are a few key differences. The ISS is not surrounded with water. So all the water it has comes from the storage it brought with it and the primates that are on board. A space crew is the living embodiment of waste not, want not. Every drop of moisture, be it urine, sweat, etc., is collected through the various systems where it can be purified into water and used for atmosphere generation. Unfortunately, generating atmosphere is but one problem for accommodating our crew of astronauts. When you hear the word terraforming, your first thought probably goes to Mars. The home of invading aliens in classic sci-fi, the Martian landscape feels the most familiar to the casual astronomer. First off, you can actually see Mars with a consumer-grade telescope. It doesn't look all that exciting, but a big rock in space seems like a solid foundation for a colony. Get it? Because it's a rock. Solid foundation. Assuming we solve both the atmosphere problem and the water problem by bringing sufficient supplies with us to sustain the limited number of people for our expedition, we'd run into other problems. Because Mars' core has been cold for a long time, the planet does not have a magnetosphere like we have here on Earth. If you've ever interacted with a compass, you've observed one of many effects the magnetosphere has on our existence. On Earth, deep below the surface is a molten metal core that continuously flows. This flow generates the magnetic field that composes our magnetosphere. It has far-reaching applications for navigation, as anything based on a compass heading aligns itself to that magnetosphere. Even in cases where GPS or satellite navigation is employed, a compass may often be used as a low-tech redundancy. The biggest benefit of the magnetosphere, though, has only recently been understood, and it has a beautiful side effect. The aurora borealis is the result of high-energy particles being intercepted by the magnetosphere. As these particles come into contact with the magnetic field, they are carried towards the poles and accelerated toward the planet's surface. They then collide with the ionosphere, which causes them to emit light. The magnetosphere redirects enough of these particles to prevent the particles and solar wind from carrying away our atmosphere. The particles that do hit the upper limits of the atmosphere in turn charge those particles and create the ionosphere, which acts as a secondary layer of protection. Without these two critical elements, we would be exposed to much more radiation and cosmic rays. Mars has neither of these because the core is cold. It has no magnetosphere, and without that, it's theorized that any atmosphere it did have was simply blown away by the sun. Having very little atmosphere means that a colony would need to maintain a pressurized environment to survive. Without somehow kickstarting the core, it's unlikely that Mars could ever be given an atmosphere by wayward explorers, as it would simply blow away. Furthermore, EVA suits would be a necessity to avoid being cooked by radiation anytime you leave the habitable zone. It's possible that some future explorers may find a way to get the core spinning again. If they do, then terraforming Mars becomes a more plausible reality. Except for one thing: gravity. Mars is rather small compared to Earth, where we enjoy a gravitational constant of 9.81 meters per second squared. Mars, on the other hand, has a constant of only 3.73 meters per second squared. This means that if, like me, you have no hope of dunking a basketball, on Mars, you might stand a chance. If your legs produce the same force, you'll jump much higher on Mars than on Earth. Your body will experience less downward force overall, meaning that you will initially feel lighter, at least while you acclimate. That might sound fantastic, and people with aging joints might feel like that is a dream come true. However, our bodies are evolved specifically for our planet's gravity. Let's take a look at your circulatory system. Arteries that carry blood away from the heart let gravity help with a lot of the downward travel. This is reflected in our overall proportions, where significantly less of our body sits above our heart. Since our heart can only produce so much head as a pump, our physiology is optimized so that the upper portion of our body is within what the heart can sustain. The veins that return blood up to the heart have check valves along their length that prevents the blood from backflowing and also keeps it progressing up to the heart. Many of the processes that your body does every day requires the variables it was originally programmed with. This includes gravity. If these variables are suddenly changed, it has dramatic effects on our physiology. Astronauts experience a significant redistribution of their internal blood volume resulting in puffy facial features and skinnier legs without sufficient gravity to pull the blood down as we expect. Long-term effects can result in circulatory deconditioning, since the heart doesn't have to work as hard in space, it gets lazy. And this can make for extreme discomfort returning back to Earth, but if left unchecked, could actually be fatal. When astronauts return, they also experience bouts of dizziness and fainting as their heart got used to that reduced workload. And reduced workload also occurs for the bones and muscles of the human body, and significant atrophy has been observed in astronauts as well. There's a host of other neurologic conditions ranging from nausea to vision changes related to physiological changes from a microgravity environment. Perhaps, if the astronauts stayed indefinitely, then these may not be an issue in their new environment. But without the ability to return home ever for fear of possible life-threatening conditions, good luck getting anyone to sign up. It's not yet known if the gravity on Mars is low enough to have such significant repercussions, for the simple fact that we haven't been there. It stands to reason, though, that while possibly less impactful, there would still be significant changes. For our terraforming crew, there's not a whole lot that can be done here. We can't increase the gravity of Mars without adding to its mass to such a degree that it rivals Earth itself. While some futuristic society might be able to swing that, it's certainly a difficult thing to pull off. An alternative to gravity could be using centripetal force, where by spinning your environment you can create the illusion of gravity pushing you to the perimeter. This is usually depicted as a solution in space, but it could be used on a planetary surface as well. Due to the high complexity of massive spinning ecodomes and severe restrictions on usable planar space, in addition to added structural challenges, it's probably better left as a temporary solution for satellites and spaceflight. So it's starting to seem like terraforming Mars isn't a great option. But it's not our only choice.
There is another.
If we look towards the Sun, our other neighbor, Venus, has some significant advantages.
I'm your Venus, I'm your fire, your desire. Introducing Venus from Gillette.
Not that Venus, this one. Venus is much closer in size to Earth and has a gravitational constant of 8.87 meters per second squared. All of the physiological concerns we had with Mars are essentially gone here. It's not without challenges of its own, however. The surface temperature of Venus is about 460 degrees Celsius. There is no liquid water on Venus, as water evaporates at 100 degrees Celsius. The atmosphere of Venus is also highly toxic, being 96% carbon dioxide. This is actually a big part of why Venus is so hot. This intense concentration of CO2 lends itself to a very powerful greenhouse effect where a much higher portion of the sun's heat stays with the planet. Venus is so hot, in fact, that not even our robots want to stick around. The longest record for a Venusian probe goes to one of the Russian Venera probes, and it only lasted less than 2 hours. If you want a physicalized metaphor for what hell must be like, look at Venus. Oh, did I mention the sulfuric acid rain? Well, not rain per se, because again, hotter than hell, but droplets of sulfuric acid hang in the air just waiting to dissolve anything it comes in contact with. In spite of all of this though, Venus actually seems to be very attractive as a colony planet. It has the most difficult variables already accounted for. The gravity is very comparable to Earth, and because of the extremely dense atmosphere and molten core, Venus also has the critical ionosphere and magnetosphere that would act as protective layers. At the surface level, the pressure of that atmosphere is equivalent to being 1 kilometer underwater. Too much for the meat puppets to survive, but futuristic robotic crews would stand a chance if we can fix the heat and acid problem. NASA actually produced a theoretical plan called HAVOC for High Altitude Venus Operational Concept. This would have human colonies occupying lighter than air floating platforms 55 kilometers above the surface. At such an extreme altitude, the atmosphere of Venus is surprisingly hospitable. The temperature up there is 27 degrees Celsius with an average pressure of 0.5 bar. This is about equivalent to being 5,500 meters above sea level. Because of the extreme density of carbon dioxide-rich environment, a floating dirigible with a breathable atmosphere is actually lighter than the ambient air. So instead of requiring a massive supplemental reservoir to achieve lift, occupants would actually be inside the bladder, breathing just fine. As for the toxic sulfuric acid hanging around, we humans have developed a number of plastics that would work quite well as protection, such as PTFE or Teflon. It's entirely possible that a future civilization would push that even further and reduce the need for any reapplication or maintenance. And earlier, we mentioned the importance of not wasting anything we bring with us. That's still true. But since Venus does have an atmosphere, it grants us certain abilities we would not have with a Mars option. For instance, CO2, while toxic, still contains oxygen. If we can extract that oxygen, then we will have carbon and oxygen. And both are valuable materials to have. So what might this look like? In our colony ship, we'll want to bring water, algae, and table salt, or sodium chloride. We start by reacting the salt and the water to produce hydrogen, chlorine gas, and sodium hydroxide. Before, when we did electrolysis, chlorine gas was a bad thing, but now we're going to use it in a chain of reactions to get more atmosphere and take care of the sulfuric acid for good. As we start collecting the acid from the air, we can then react it with our sodium hydroxide to create water and sodium sulfate. This is great because we got our water back. Now we take advantage of the vast amounts of CO2 around us and react it to our hydrogen gas. This gives us methane and more water. More water is more good. Methane is less helpful, but it can be used as a propellant with enough oxygen. If only we had a way to turn vast amounts of CO2 into oxygen. That's why we brought the algae along. Algae is great because it photosynthesizes just like any other plant. But because there's such a variety of algae species, finding or creating one that is suitable for Venus is a lot easier. While we've been eliminating sulfuric acid from the air, it will have been producing oxygen from the abundant CO2. It's also storing carbon in its physical structure, which would later be used for building materials. If we burn the methane in an oxygen-rich tank, we get water and CO2 as a result. This is fantastic news because we've increased our water supply, reduced sulfuric acid from the environment, and converted valuable resources. We still have one more step to close our circuit, and that is to take our sodium sulfate from before and heat it to 1000 degrees Celsius, where it will decompose into sodium gas, oxygen, and sulfur dioxide. If we let the sodium and chlorine mix, we get back our salt and can begin the whole process again. This is, of course, highly simplified for the purpose of this video, but it illustrates the kind of creativity that would need to be employed to sustain life on another planet. Assuming we've been successful with our Venus venture so far, it's possible that we can start expanding our structure using the carbon and other materials we've harvested. By this point, it's also possible that we can send robotic crews down for short scavenging runs to collect resources from the surface. This would be a valuable source of metals and other elements to facilitate further expansion. With a colony now living in high-altitude Venus, we can also coordinate further supply drops from Earth to deliver critical components as we build up native manufacturing and resources. At some point, it's also entirely possible that the Venus colony is self-sustaining and also a net producer of goods capable of sending supplies back to Earth. Compared to Mars, we have a shorter travel distance, more frequent travel windows, and easier access to base elements for space travel. Because we've been processing a lot of sulfuric acid, we can divert some of our production to create hydrogen fuel for rockets.
Hydrogen fuel is at 100%.
Additionally, hydrogen is special for its potential in fusion reactors. While solar and geothermal, or would it be aerothermal, are both great options at the beginning, fusion reactors would be the end goal for power production, just as it is here on Earth. It's clean, produces no harmful byproducts, and could potentially give us access to more of the periodic table while on Venus. Given enough time and luck, the end stage of Venusian exploration would see algae-covered floating metropolises floating a little closer to the surface. Having eliminated the sulfuric acid from the air and converted vast amounts of CO2, the platforms would naturally start to float just a little closer. Ideally, we'd get it to the point where we have a comparable atmospheric pressure. If at such a point we have our floating cities at the right pressure and without any other nasty thing hanging around, then we might actually see a city much like Orison from Star Citizen or Bespin from Star Wars. We'd be able to walk freely and breathe the atmosphere we created for the planet. Such an advanced floating city would see farming take root as supplies get replenished by robot crews that now have a much easier time navigating the cooler surface with a lower temperature as a result of reducing the CO2 and greenhouse effect. Such a dramatic change on a planetary scale may seem far-fetched, but it's not outside the realm of possibility. After all, aren't we affecting our planet today? This is also only one possible means of colonizing Venus. Kirsgasat has also made a great video specifically on the topic of terraforming Venus, but takes a very different approach. If this subject interests you, I highly recommend watching their video as well. One thing I want to stress is that in all the cases we've looked at so far, the goal has been to create Earth-like environments on other planets. That's a noble goal and makes a lot of sense because, after all, Earth is our home. However, it's not the only option. Terraforming, by nature of its definition, does mean to create other Earths, but the wider definition of colonization is not as stringent. If we as a species created a fully autonomous manufacturing plant to supply us with resources from another planet, is that not also part of colonization? Right now we are limited to robots with a single lifespan and limited service life. But what if we created a self-replicating army of robots that can operate indefinitely without our intervention? Such a feat would enable us to land on Saturn's moon Titan to process the vast stores of water ice on its surface. There's not a lot of value in establishing a colony of people there. There's very little light, it's super cold at minus 180 degrees Celsius, and the surface is mostly methane seas and water ice masses. We used methane in part of our reaction chain on Venus, and we can react it with oxygen to create CO2 and water. It can be used as a propellant, and so these methane seas are like a giant gas station waiting to be tapped. Even more useful is all that ice there. Ice, ice, baby. As we already know, water is hard to find. Titan has more than twice the water of Earth combined. So instead of having it literally chill there, a spacefaring species could ship Titan's ice to other project sites to supply them with water. By automating a robotic colony on Titan, we could have vast stores of propellant and water for our ever-expanding list of projects. We just don't want to live on Titan ourselves. It has a similar gravity to our moon, and therefore not good for long-term exposure, and the lack of light and heat are not conducive to carbon-based life forms as we know them. But no one cares what robots think, so we can just send them there instead and still reap the benefits. This is part of the wider vision I want you to open your eyes to. It's not just planting a flag on some distant shore or raising a farm on another planet. Our step into being an interplanetary species comes with a host of benefits. From Titan, we'd have tons of mineable water for projects and more propellant than we yet know what to do with. From Venus, we'd gain a second home that could eventually be a massive floating terrarium. Commerce and manufacturing split between these locations could allow us to usher in a massive increase in wealth and the ability to offshore less desirable processes away from human populations. Imagine what kinds of experiments could be conducted at large scale without the danger of affecting our population. People get queasy about the colliders we've built already, so why not make a remotely operated one on an otherwise inactive moon somewhere else? Each branch from the main Earth colony also opens up new networks of space launch windows. Remember when that asteroid of gold came through our solar system? Even if we had the technological ability at the time to capture it, it's very possible we'd be missing a suitable launch window to do so. Every spaceport at a new celestial body deepens our ability to take advantage of these kinds of opportunities. Imagine a fully automated manufacturing hub on Mars with minimal interaction, far from human life and in an environment where the low gravity enables more efficient production methods, all without fear of contaminating a non-existent atmosphere or poisoning our precious seas. We could have paradisical worlds on Venus and Earth and ship the consequences where life can't exist anyway. At some point, we may even use our gas giants as a trash compactor. In the far distant future, where mankind is a master of our solar system, we can visualize an ever-expanding horizon where human hands are spread across our galaxy. In this distant future, with trillions of human souls out there, I just might find somebody to love.